Imagine a patient in a rural clinic trying to describe a sudden, sharp chest pain to an AI diagnostic tool. They might use local slang, they might speak in a heavy regional dialect, their voice might tremble, or they might just hesitate for a second. A local doctor picks up on all of those cues instantly. But an AI system, it often completely misses that context, leading to potentially dangerous misdiagnoses. Okay, let's dive into this, because today's explainer covers a groundbreaking piece of research that tackles this exact, enormous blind spot. We're looking at HEALTHDIAL, a massive new dataset designed to break the speech data bottleneck in global health AI. Here's our roadmap for this explainer. We're going on a chronological data journey today. We'll start with 1, the speech data bottleneck, then 2, introducing the HEALTHDIAL dataset, 3, a 4-step creation pipeline, 4, linguistic diversity and demographics, 5, benchmarking the AI pipeline, and we'll wrap up with 6, user trust and the future.
All right, let's jump straight into Section 1, the speech data bottleneck, the hidden bias in healthcare dialogue systems.
Which brings us to a really fundamental question. Why on earth does global health AI often ignore local accents and dialects in the first place? Well, the answer lies in how these systems are traditionally built. They use what's called a modular pipeline. First, an automatic speech recognition tool converts your voice to text. Then, a text-based model generates a response. And finally, a text-to-speech tool reads it back out loud. Now, while this works mechanically, this process literally normalizes away crucial sociolinguistic variations. When a system flattens spoken language into standard, plain text, we lose incredibly valuable diagnostic context. A patient's hesitation, their unique phrasing for a specific symptom, the subtle tone of pain in their voice, it all just gets wiped away. It completely robs the AI of the reality of how human beings actually communicate when they're sick.
And it gets worse. To quickly build AI for other languages, researchers often take a major shortcut. They just directly translate English datasets. This creates something called translationese. Basically, translationese refers to those unnatural language patterns that pop up when you directly translate source material. So the crucial point is, simply translating English datasets is a deeply flawed approach for healthcare. Think about it. When you feel terrible and have a fever, you don't speak in perfectly structured, highly formal textbook grammar, right? You use natural conversational shortcuts. But a translated dataset often sounds robotic and overly formal. It bypasses how native speakers actually converse, reduces the naturalness of the dialogue, and falsely inflates how well developers think their AI is performing in non-English languages. We desperately need a better way.
That brings us to Section 2, introducing the HEALTHDIAL dataset, a multi-parallel, multilingual solution.
The scale of this solution is seriously impressive. HEALTHDIAL is not just another translated text file. We're talking about 6,000 multi-turn information-seeking dialogues. That is 1,500 completely unique conversations per language across Arabic, Chinese, English, and Spanish. It packs in 163 hours of actual native speaker audio. And critically, this is absolutely huge. Every single medical response in this dataset is grounded in trusted, verified knowledge snippets from the World Health Organization. Why does that specific detail matter so much? Because in healthcare, an AI hallucination, where the system just confidently makes something up, isn't just a quirky tech glitch. It's a massive liability that could genuinely harm a patient. Grounding this entire dataset in verified WHO facts is what turns it into a safe, reliable medical tool rather than just a fun conversational experiment. It completely sidesteps that translationese trap we just talked about.
Moving right along to Section 3, a 4-step creation pipeline, from abstract schema to naturalistic speech. Let's look at exactly how they built this. So the journey starts right here with verified web pages. In high-stakes domains like healthcare, reliable data is quite literally everything. By scraping specific questions and answers and fact sheets directly from the World Health Organization, the researchers ensure the AI has a rock-solid, hallucination-free foundation to draw its answers from.
From that verified data, the team engineered a highly specific 4-step pipeline. 1, knowledge-based construction, 2, pilot experiments, 3, dialogue schema creation, and finally 4, surface realization.
And this brilliantly illustrates the entire flow. Honestly, this pipeline is the absolute heart of the research. So let's break it down. Starting on the far left with Step 1, those WHO snippets are extracted into a clean knowledge base. Moving into Step 2, the team ran pilot experiments. They had human users interact with ChatGPT to identify 11 core dialogue acts. Things like a standard greeting, presenting a health concern, or asking for a clarification. Now, moving to Step 3. Rather than just asking an AI to write a script from scratch, which usually sounds super robotic, they mapped out the structural flow of a conversation using what's known as a Markov chain. In simple terms, a Markov chain is just a mathematical system that decides the next logical step in a conversation based on the current state. It makes sure the chat flows naturally and doesn't feel rigidly scripted. These abstract conversation structures, combined with the WHO data, were then used to prompt a large language model to create hypothetical English dialogues. But the true genius of this research is in step 4. They didn't just translate those English dialogues. Instead, they extracted the core intent of each line into what they call improvisational prompts. They handed these intent prompts to native speakers using a custom annotation tool and essentially asked the humans to act out the scenario in their own natural speaking style. They didn't hand them a rigid script, they handed them a motivation. That is exactly how they captured true, authentic human speech and emotion, all without ever compromising real patient privacy. It's really clever.
Which leads us nicely into Section 4, Linguistic Diversity and Demographics, Capturing the Human Element.
Because speech data is fundamentally human, you have to capture a true global representation. And this dataset captures an incredible 19 distinct language varieties. They didn't just check a single box for Spanish or Arabic. If you look closely at the breakdown here, you'll see everything from Egyptian Arabic and Levantine Arabic to Min Chinese to Peninsular and Andean Spanish, right alongside various regional English dialects. This is a massive deal. Treating a language as a monolith is a huge mistake. Andean Spanish, for example, is vastly different from Peninsular Spanish. The vocabulary, the phrasing, the acoustics, it's all different. By capturing this level of granularity, the researchers ensure that any AI tested on this data actually has to contend with real-world acoustic diversity.
Accompanying all of that native audio is some incredibly rich metadata. Every single speaker's gender, age range, region of origin, and education level is meticulously tracked. And tracking this matters deeply because, well, human language is messy and wonderfully complex. The researchers actually found that the human-authored utterances in this dataset were much longer and far more lexically diverse than anything the AI generated. Lexically diverse just means that human speakers use a much richer, wider vocabulary, full of unpredictable phrases, whereas AI tends to sound repetitive and sterile. Tracking all of this demographic metadata is exactly how we prevent AI from being biased against certain education levels or regions down the line. It's how we ensure fair healthcare tools for absolutely everyone.
Okay, Section 5, Benchmarking the AI pipeline, revealing the stark disparities. We have this incredible data set now, so how do current AI systems actually perform on it?
Time to look at some hard numbers. This benchmarking data tells a very compelling and frankly a somewhat troubling story. We are comparing AI performance across Arabic, Chinese, English, and Spanish. Let's walk through exactly what we're measuring here. The first metric is word error rate, or WER, for automatic speech recognition, where lower is better. Next is MCD, or cepstral distortion, which essentially measures the audio distortion during text-to-speech generation. Again, lower is better. Then we have turn classification accuracy. Moving to the right, we measure knowledge retrieval using a metric called R at 10, which tracks how well the system fetches the top 10 relevant WHO documents. Finally, we have EM, or exact match, measuring how perfectly the system filters down to the exact correct medical answer. Now, just look at the board. Notice how the performance fluctuates widely depending purely on the language. The medical scenarios are entirely parallel, yet the AI's ability to actually handle them is incredibly uneven. Now, what's really interesting about this slide is the stark contrast. We've isolated the highest and lowest performers to make it clear. For high-resource English, the speech recognition word error rate is an incredibly low 0.03, but for Arabic, it's 0.23. That means the system struggles significantly more just to understand the basic spoken words of an Arabic speaker. Furthermore, when tasked with filtering an out-of-knowledge query, the exact match rate for Arabic in some models literally drops to 0.00%. Let that sink in for a second. An exact match rate of literally 0 means that if an Arabic speaker asks a critical, out-of-bounds health question, the system completely fails to filter it correctly. This highlights a severe, ongoing inequality in current state-of-the-art AI models and points to a massive risk of misdiagnosis for non-English speakers.
And listen, this isn't just a problem with one specific, older model either. This bar chart compares the exact match percentage across different iterations of large language models, specifically the GPT family. Even as we move to the absolute most advanced LLMs on the far left, the deductive reasoning capabilities leave a lot of room for improvement. The AI still struggles to consistently pinpoint the exact correct medical snippet from a list of candidates. But crucially, the performance gap between English, represented by the green diamond, and Arabic, represented by the blue dot, persists across every single model iteration. This proves that simply throwing more computing power or newer models at the problem, it doesn't fix the underlying language inequality.
So, what is the actual human impact of these technical shortcomings? Let's shift our focus to our final section. Section 6, User Trust and the Future. Where do we go from here?
To understand the real-world viability of all this, the researchers conducted a human evaluation of a prototype dialogue system. They used what's called the TAM2 framework. That stands for the Technology Acceptance Model, which is just a standard way to measure how users come to accept and use a new technology. Now, the shape of this radar chart reveals a ton about the tension in medical AI right now. The system scored quite high on the right side for perceived ease of use and perceived usefulness. People generally found the interface helpful and simple to navigate. However, look over at the left side. The score for trust in system is noticeably pulled in, and the system overall satisfaction lags significantly behind the baseline satisfaction users have with the actual WHO website. This perfectly illustrates a massive hurdle we're facing. Even when an AI is perfectly easy to use, it doesn't automatically mean people trust it. And as we all know, in healthcare, trust is the absolute currency of success.
And speaking of trust, it is so vital to remember how this dataset was built. As the research team states, the dataset consists entirely of hypothetical dialogues with predefined content, thereby minimizing the risk of unintentionally including personal data. It is absolutely critical to emphasize the word hypothetical here. By using expert-crafted scenarios and actors, this methodology brilliantly sidesteps the massive legal and ethical nightmares usually associated with harvesting real medical recordings. The researchers managed to create an incredibly valuable tool for medical AI without ever violating the privacy of a single real patient. Which leaves us with this final thought for today. HealthDial has brilliantly exposed the flaws in our current systems, yes, but it has also provided the exact tool needed to fix them. So the question I'll leave you with is this: how will developers use this benchmark to finally close the language gap in global health AI? This isn't just a technical problem anymore. It is a challenge to the entire tech community to really think about the future of global healthcare equity. Thank you so much for joining me on this explainer. Keep learning, and I will see you next time.